In week 3, we'll be looking at setting up a couple different types of simulation networks and DOPs. We'll be looking at pop particle sims and vellum grains. So this disintegration of this foreground creature here is happening with vellum grains. But first we're going to look at the particle sims, and we're using those particle sims to animate these little small, I call them mechanical bugs for this shot. Yeah, these little guys flying around in space with these particulate trails coming off of them. Those are simulated in POPs, which is a slightly more simple type of simulation to tackle than, for example, vellum sims or RBDs or etc. So pop particles is a good place for us to start here. And we'll start just by simulating some points for the motion of these little small guys flying through space. And then we'll do the particle trails separately after that. So let's dive back into our scene here. And I've created a geometry object called particle flyers. And before we set up the exact simulation for the mechanical bug creatures, I'm going to just first cover how to set up particle sims in general and show a different couple ways of handling the sourcing from those sims. So let's create a sphere to source particles from, and we'll bring this off of the ground, just raise the center a bit, and all of our simulations will take place inside of DOP networks. And there are alternatives to just using a DOP net for lots of different types of simulation. There are wrapper objects that allow you to run the sims without setting up all the elements of the DOP net directly. So for example, when we get to do bullet sims, there's an RBD bullet solver, and this has a DOP net inside of it, and this just makes it faster to set up RBD sims by using this instead of doing the DOP net manually. Similarly, we have Pyro solver as well. This also has a DOP net inside of it, as does the vellum solver. But for pop particles, at least at this point, we don't have a wrapper available for those. And pop particles are a bit easier to understand and set up than the other types of simulation, so it does serve as a good starting point for learning your way around DOP nets anyway. Perhaps SideFX will add a wrapper for pop particle sims at some point also, but for now we have to do it manually in a DOP net. So I'm going to connect my source object to the first input of the DOP net, and then dive inside here. And the DOP net has this output node by default, which will contain the final output of the simulation, of course. And we can create any type of solver that we want to inside here. So for pop particles, we're just going to use a pop solver and wire that to the output here. And this solver needs to have an object to process. This won't do anything on its own, so we need to give this an object that will store all the data associated with the simulation. So this is going to be a pop object that stores the info about the particle object itself. And we can connect that to first input of the pop solver. And then the other two inputs for this pop solver here allow us to add additional functionality before and after the particle motion is computed. So you might want to apply some influences before it actually computes the particle motion. That's what this pre-solve input is for. And you might want to do other things after the current frame's motion's been applied, in which case that's what this third input is doing here. This is called sources, but not only can we source particles there, any sort of post-solving inputs for the current frame can be applied at this point. And we can start creating particles here by creating a pop source and wiring that to that third input there. And we have a few different types of sourcing available. On this pop source, you can see we have the default option is scatter onto surfaces, and you can point this SOP parameter to any object in your scene that you want to scatter particles onto. In this case though, because we've connected this sphere to the first input of the DOPNet, I'm not going to use an explicit geometry path. I'll just tell this to use the burst context geometry. And you can see when I select that, it's creating particles on the surface of the sphere here. And if we start playing this simulation, it's just going to add particles onto that sphere on every frame. And this doesn't look very interesting just yet because those particles aren't moving at all. So let's start adding some more influences. We can add a gravity force, and the gravity will be placed after the pop solver here, just before the output. And if we play that, yay, we've got some falling particles. And this is all well and good, but we could have a much more interesting simulation with some colliders. So let's add in a ground collision object. If you just type in ground, there's an object called ground plane, and we can merge any collision objects into our simulation after the pop solver. It doesn't really matter if this goes before or after the gravity. It's kind of flexible in terms of how you wire it in here. So let's just put it after the gravity at the moment. So we can merge this collision object with our gravity here and connect the ground plane to that. And by default, this isn't going to do anything. So if we rewind the sim, you can see now the ground plane is visible. But if we start to play this thing, then that collision's not going to have any effect whatsoever, because this merge of the pop object and the static collider ground plane, this merge has an effector relationship of the left inputs affecting right. So if you look at the order of the merge DOP here, we have the pop object on the left side of the merge and the ground plane on the right. So the left affects right means that the pop object affects the ground plane, but the ground plane does not affect the pop object because the right does not affect the left in terms of the input order here. So there are a couple things you can do to fix this. You could change the relationship to mutual, in which case that collider will start working, and you can see those particles are colliding with the ground. And that's fine, but oftentimes I will just leave this effector relationship at the default left affects right, and we can just change the input order on the merge here. So if you select the merge and hit Shift R, then that will rearrange the input order there so that the ground plane is on the left side, and now that will make our collider work as well. Cool, so that gives us one way of sourcing particles and colliding with objects. And actually, we might as well create some more interesting collider objects while we're at it. So in addition to this ground plane here, let's create some actual interesting geometry to collide with. So outside of our DOPNet here, I'm going to just create perhaps a pig head for a collider. So let's create that and template view this pig head. And I'm just going to translate that up a little bit, maybe make it a little bit bigger as well. Now we have a few different types of collisions here. We can either collide with the polygonal surface of this pig head, or we can collide with the volume representation of this pig head here. And now to get the pig head working as a collider, let's go back inside the DOPNet here, and we can create a static object. And you can merge as many collision objects together as you want before combining that into this, pop simulation stream here. So I'll just drop in a merge, and in this case, the input order doesn't really matter on the static objects that we're merging together, because it doesn't really matter if the static objects affect each other, as long as they all affect the particles. So let's just wire the static object in without caring about the input order there. And then on the static object, let's point the SOP path to the geometry we want to collide with. So I'll open up our object selector there, or I should say operator selector, And we'll point this to the test geometry pig head that we just created. You can see that's now visible in our DOPNet here. And if we play through this, we should see our particles colliding with the pig. And this is currently using surface collisions by default. It's just colliding with the polygons of that pig head. And in some cases that's fine. In other cases you might want to use a volume representation of the pig head for collisions. I'm always kind of bouncing back and forth between which collision type I'm using. And it's good to have both options available so that if you have problems with one, you can try the other. Yeah, by default here, we're just colliding with polygons. And if you select the static object and scroll down a little bit, you can see, well, first of all, we have some options for physical parameters, which I'll just show this first before we look at the different collision types. Right now, the particles are bouncing off this pig head pretty severely. They have a fair amount of bounce off of that. But if we lower the bounce on the static object parameters here, and we also have a similar thing on the ground plane object, on the physical tab you have the same sets of parameters there. And if we set the bounce to a lower value, then we'll get a much less energetic simulation because we're not bouncing nearly as much. So we can also control the effects of these collisions with our friction, and those are the two main things I mess with. I don't really use bounce forward or dynamic friction scale or temperature very much for these colliders. Usually it's just the bounce and the friction that I need to play with. So let's say that perhaps this pig head is made of ice, so that's very low friction, but the ground plane, say that's a very high friction object. So let's, on the static object, we can leave this pretty low. We're already not getting a ton of friction, but on the ground plane, let's try turning this up quite a bit and rerun our particle sim and see what sort of different behavior we have. And we're still not getting much effect of friction with our ground plane collider here. So we can also check the physical parameters on the pop object itself. So if you go to the pop object here and look at the physical parameters for that, you can see that by default the friction is 0. So it doesn't matter what we set for the friction on any of our collider objects when the friction of the particles is 0. So let's give the particles some friction on the pop object as well. And let's rewind this sim, play through it. Okay, so now we have that very low friction on the pig head, and because I was testing out the friction on the ground plane, I really cranked that up quite high. So we're getting the particles sticking instantly on contact here. So that looks a little bit silly, so let's turn our collision on the ground plane down quite a bit. Let's try a value of 2 and see what that looks like. That's still quite sticky. Anyway, we don't have to get this working perfectly right now because hopefully you get the idea at this point of how these physical parameters work here. And as I was starting to say before, we have a couple different types of collision available. By default, this is currently using surface collisions for the pig head. And if we go to our pig head static object once again and go to the collisions tab, you can see there are two different types of collisions available. You can select volume or surface, and by default, we're just going to be using surface collisions. Let's switch over to use volume. So on collision detection, let's tell this to use volume collisions. Let's turn off the display geometry for the moment, and on the volume here, let's turn on the collision guide. And you can see that this is not giving us a very nice representation of the pig head here. And we can make this a little bit better. We can increase the number of divisions on this volume creation. So let's turn that up to 100 and let's try rewinding this. Okay, so turning up the divisions for the volume collision up to 100 gives us a much better representation of this pig head here. And when we play the simulation, we should see pretty much the same behavior. Looks like it might be running a little bit more slowly perhaps. Not sure if I'm misremembering the speed from a moment ago, but in any case, we have some pretty similar results, and as I mentioned before, you can feel free to play around with using either surface collisions or volume collisions. Now, this will create a volume collider for you, as you've just seen here, and you have to turn on that collision guide in order to see what it's creating. And you can use this method where it will automatically create these collision objects for you, but generally in production we always want to have full control over the collider volume that we're using. So instead of letting this just create a volume arbitrarily for you, let's create our own collision volume. So let's go back up to SOPs here, and on our test geometry pig head, let's create a VDB from Polygon. Connect that to our pig head, and then on this VDB from polygons, you can pick whatever resolution seems appropriate for your simulation. So let's try increasing the resolution a bit. I'll turn this up to, let's try 0.06. It's still fairly low res. Okay, 0.03 gives us a very nice representation, but don't feel like your colliders need to be super accurate. You know, as you've seen in simulations like this here, a lot of times these sims are kind of chaotic, and this particle flow coming off of the pig head here, if this is not 100% accurate to the surface of your object, you won't necessarily notice. So if you're trying to create a perfect high resolution collider for your simulation, sometimes that really high res collider can slow things down quite a bit, and that can really be wasteful in terms of simulation time. So you can get pretty similar looking results with a much lower resolution collider than this. And this is one of the reasons why I always like to create my collision volumes and SOPs instead of doing it within DOPs. And you can, of course, control the resolution and everything inside the DOPNet, but SOPs gives us so many nice VDB operations to sculpt the colliders exactly how we want them. So, you know, for example, maybe this collision object is giving us more detail than we really want in the surface of this pig. Perhaps you're seeing particles getting trapped in this little like neckline here, or you have particles getting trapped in that ear, or maybe the mouth creases or something. We can always kind of round out these collisions a little bit more to remove some of those areas. So let's do a VDB reshape on this. And the default operation for a VDB reshape will be to dilate and expand that. So let's increase this a little bit more. And that's kind of effectively rounding out our shape quite a bit. And let's create another copy of that VDB reshape. And then for this one, I'm going to leave the same amount and switch the operation to erode. So that kind of smooths out the shape a little bit. And if we compare the original VDB to the version after dilating it and eroding it, it kind of gets rid of some of those creases. It's sealing up the mouth area, so that will prevent particles from going inside the mouth here. You know, these sort of VDB operations give us a lot of control over the behavior of our collision objects. So this can be very helpful. In addition to reshaping with the dilate and erode, we have lots of other operations available as well. For example, you could use a VDB smooth SDF, and that will kind of do some similar things to dilating and eroding. As always, it's good to have multiple options at your disposal to see what works what best for any given situation. So on this VDB smooth SDF, we can perhaps increase the iterations to smooth that result out some more. In this particular case, I think we're getting a bit too far away from our original shape here. So after smoothing it out some more, we could continue to massage this VDB shape and do some extra dilation on it to get it closer to our original shape. But at this point, I think we're kind of introducing more inaccuracy than we need. But remember, your colliders don't have to be super accurate, so only feel like you need to put as much collision accuracy in there as you'll actually see represented in the sim, keeping in mind what it'll look like when it's rendered with motion blur and everything else in the shot. But still, I think this smoothed SDF and the dilation on that doesn't look quite as nice and accurate as just doing these two sets of reshapes here. So I'm going to use this volume as a collider. So let's create a null here, and I'll call this collide pig. And then inside the DOPNet, we can tell the static object to use this volume in SOPs explicitly instead of creating its own volume for that collision. So inside the DOPNet here, right now we're back to our default volume collider settings on this static object. So let's change the mode to, instead of doing array intersect, we'll just do a volume sample so that we can directly sample that volume that we've created in SOPs. And then scroll down to the proxy volume, and let's point that to that collide pig null. So this volume collider here is exactly what we've created in SOPs, and instead of the DOPNet building its own volume on every frame in order to create that collision shape, it's sampling that directly from SOPs here. So I definitely encourage you to build your own volumes when you use volume collisions, and as you can expect here, this simulation behaves similarly to before, just with our own custom collision shape now. So that all looks right, and in this particular case it actually does look like it might be running a little bit slower with volume collisions. Just to do a quick non-scientific test for this, we can switch this back to surface collisions, and I'll turn on the display geometry once again. Let's rewind here and then play through this once again. Yeah, it looks like our surface collisions is about the same speed. We're not testing this very scientifically, but it looks pretty similar in terms of our interactive view here. If you do want to really get scientific about comparing the different evaluation speeds of different parts of your setup, you can use the performance monitor to check that. So let's reset our simulation here and go to our DOPNet simulation tab. Let's hit reset on that. Let's display the DOPNet first and then pull up the performance monitor. So go to Windows and Performance Monitor, or just hit Alt-Y on Windows, and then you can hit record for this to start monitoring the evaluation time of your scene. So let's hit record, and I'm just going to change this to frame, let's try 75. So that was very quick to cook that simulation up through frame 75, and this gives you the time that it took to evaluate all these different parts of the network. So this took an overall time of, looks like 3 seconds here, and we can stop this recording, and you can see this is also colorizing different parts of your network here to show you visually which areas are the slowest to evaluate. And if you want to get rid of that, you can just hit record once again and hit stop again, and that will get rid of this color feedback in your network view here. And if we want to compare the evaluation time to the volume collisions, we can switch this collision detection back to the volume option. Let's rewind here, get out of our DOPNet, reset that sim at frame 1, and now let's hit record once again, jump ahead to frame 75. So it looks like in this particular case, the surface collisions ran quite a bit faster. This only took 1.74 seconds instead of 3 seconds. Yeah, in this particular case, the surface collider was quite a bit faster, but this is affected by lots of different things. The resolution of your surface will make a big difference as well. So let's, for example, subdivide our surface quite a bit to see how much that will affect the evaluation time of that collision. So let's get rid of that colorization here. So let's bring up our performance monitor once again, hit record and stop to get rid of the display there. And then on our pig head, I'm going to subdivide this a few times and see how that affects the simulation speed. So let's drop in a subdivide, wire the pig head into that, and then on the depth for the subdivide, let's try subdividing it 4 times, which will be quite high resolution. And you can see that's, much higher res than before. This is what it was. This is what it is now. We've gone from under 3,000 polygons up to 738,000. So let's create a new null to point to this updated collision shape. So I'll call this collide pig mesh. And let's compare the simulation speed with that cranked up collision density there, or I should say that mesh density. So let's rewind our sim once again. And in the DOPNet here, the static object is currently pointing to the test geometry directly, but let's change this to point to collide pig mesh. And you can see our DOPS display here is showing us that high resolution mesh instead. Even though we're no longer using volume collisions, actually it looks like this is still set to use volume collisions. Let's go back to surface collisions here. And you can see that this volume is displaying regardless of what collision type we're using. So don't let that display confuse you too much. That's controlled by this collision guide setting on the volume tab there. So if you want to turn that off, let's turn on volume collisions and turn that collision guide off there. And then go back to surface collisions once again. And then we can see how much this collision mesh resolution affects the simulation speed. So let's finally dive out of our DOPNet once again, display that particle sim, and let's bring up our performance monitor again. And I'll hit record and stop to clear that out. Start recording again. Set this to frame 75. And this is taking quite a bit longer. We're already at 15 seconds on this DOPS evaluation here. So you can see that this is definitely taking a lot longer than when we were colliding with the low resolution pig head before. So as I mentioned, the best collision option can vary depending on what you're colliding with. And you may need to play around with this to find the best option for your simulation. I'm just going to cancel this now because with this high resolution pig head collider, we're already over a minute and this is not finishing. So I'm just going to kill that simulation there. And in this case, we're getting much better results, at least in terms of simulation speed from the volume collisions. So I'll leave it set to that with its volume sample option.